I think we'll make a start then. Let me welcome you to the 5th seminar in our series on global warming. Our speaker today is Jasper Kirkby, who comes to us from Switzerland, the CERN laboratory just outside Geneva, and he is, of course, a particle physicist by background. Jasper took his first degree at Oxford, followed by his doctorate at the University of London, and then he spent 12 years at the Stanford Linear Accelerator before moving to CERN in 1984. He's been directly involved in the development of major detector systems and the experiments stemming from them at a wide range of accelerator facilities around the world, including the Brookhaven National Lab, SLAC, of course, CERN, and the Paul Scherrer Institute near Zurich. He's also credited with having had the bright idea for a Tau charm factory. And I'm quite sure you wish you had one too. This led directly to the construction of the Beijing electron-positron collider, which I believe opened in 2006.
Well, the upgrade of that machine.
Right. Today he's the head of the cloud experiment at CERN, and so that's what he's going to be talking to us today. He brings a very different perspective to the question of global warming, in that he is a particle physicist by background, and I'm sure you'll find his talk extremely interesting. Jasper.
Well, thank you very much for the introduction, and thank you, Colin, for the faculty for inviting me here to give this talk. Yes, I'm a particle physicist, but I've become, over the last 10 years or so, very deeply involved in an experiment which I originated at that stage, which is called CLOUD, and it's concerned with whether there's a connection between the cosmos and Earth's climate through clouds. Now, I have to say at the outset, we don't have the answers. We don't know if this is a fact. But there's a lot of motivation, scientific motivation, and I'll try and transmit some of that to you, that's been obtained. And we've just started measurements. We actually started with this experiment at the end of 2009, and we have our first measurements. And I'll give you a flavor as to what we're starting to find. But anyway, let me go into the talk. So just to set the context for this, and I'll go quite quickly through these first few slides, because I know you've been saturated by IPCC stuff over the last few weeks. So all this is super obvious to you. But this is the global warming over the last century. The particular thing I want you to take note is it's not just a warming that's happened since 1975, but there was an equivalent warming of roughly the same magnitude and steepness in the first half of this century. Okay. Now, the total contribution, the so-called forcing agents that have been responsible for this, according to the IPCC, they sum out at 1.6 watts per square meter, and the major contributor are the greenhouse gases, but mankind has also thrown up aerosols and precursor gases, which have caused a cooling effect. These have big errors. But anyway, that's the bottom line. The understanding is that this is almost totally caused by mankind. It's about 1.6 watts per square meter of initial forcing. But very importantly, the IPCC and everyone, I think, on all sides of this climate debate agree that the understanding of aerosols and their effect on clouds is very poorly understood. Now, just to make sure absolutely everybody in the audience is very familiar, because I'm afraid you're going to hear the word aerosol several times in this talk. Aerosols are small clusters of particles, a few tens or hundreds of nanometer, that are suspended in the atmosphere. They're typically a few hundred to a few thousand per cubic centimeter, or even more in polluted atmosphere. They're extremely important because they scatter sunlight, but much more importantly, they form the seeds for cloud droplets. If there were no aerosols in the sky, there would be no clouds in the sky. So all clouds form on a particular seed. And when those seeds are present, if the relative humidity goes above 100% by just a few tenths of a percent, then clouds will form. Okay? So these are the various contributions to this global climate temperature change. And let me just draw your attention to one particular thing. The solar irradiance is thought not to have changed much, very slightly over the course of the century, but essentially dominated by this very small oscillation due to the sunspot cycle. But there's been a small net increase, just the average radiance, but it's very, very small. But essentially, the first part of this century, there was no contribution from mankind's greenhouse gases and so on. And that, you see, leads, even though it leads to a good agreement in the second half of the century, I would maintain that this is rather a poor representation of the data, the current models, and that's shown there. But the solar contribution, which is going to be the topic of this particular talk, is definitely there. If you look at the sea surface temperature, this is the blue line. This is quite small. This is plus or minus at 0.5 degrees. Excuse me. Then you see the sea surface temperature oscillating, and it oscillates essentially in phase with the solar cycle, actually with the irradiance cycle. And it has the right frequency and the right lead and so on. It's heavily damped because the oceans can't respond over a 10-year cycle to this forcing, and that's why it's a much smaller effect. Excuse me. Sorry. Okay, so there is a solar signal, but it's thought to be very small, and that was shown in the previous slide. It's thought to be only 5% of the contribution from mankind, from the greenhouse gases and so on. So clouds are very important. You're well aware of all this. They have a net cooling effect, and you can see that a very small fractional change of clouds could have a significant climate effect. And in fact, there may have been some changes in the cloud cover. We don't know, and these data are very poor, but this is what it shows over the last 20 years. These are various reconstructions of the so-called albedo of the Earth. This is this is what the Earth would look like in terms of its reflectivity. It would be below roughly 10% if there weren't any clouds in the sky. But the presence of clouds causes a reflection of about 30% of the sunlight that comes in. So it's a very, very substantial effect. And the question is, has this changed for any reason, systematically changed? And there are indications from several different measurements here. They're very difficult to make. They have big errors. They're independent measurements, but they certainly have huge experimental errors. But there seems to be some warming trend, decrease in clouds over the last 15 years or so, and an increase perhaps, although there's a divergence in the data, over the last 10 years. Just to set the scale of this is the contribution of greenhouse gas warming over this period. It's about plus 1 watt per square meter. So you can see if there really is a decrease of clouds here, that could have contributed to the warming that we've seen over that period. It's simply reflecting the lack of understanding that we have of clouds at the moment. Now, this cartoon is actually expressing, this is, you could say, the summary of what my talk is going to be. I have to say something about the sun. Well, this is the possible mechanism that cloud is going after. And there's a very important question mark there. Please do not think that this is an established process. It certainly isn't. There's a big question mark there. We don't know whether this is happening, and that's why we're doing cloud, why we need to do the measurements. But cloud is hoping to answer the question whether this process happens or not. And in particular, it's answering this little corner here. But let me just point out the elements. So that basically the sun has its irradiance, which is warming the Earth. It also has the solar wind, which is the plasma that streams off the sun. This is responsible for partially deflecting cosmic rays, which are basically produced in supernovae in the Milky Way. It partially deflects them and alters the intensity of cosmic rays reaching the Earth. The big question is, do these cosmic rays affect cloud formation on Earth? If they do, then clouds can have a very big effect on changing the insolation, the amount of sunlight that reaches the Earth, and there could be a climatically significant effect. So let me sort of quickly go through some of those elements. We'll look at solar and galactic cosmic ray variability. Clearly, what we're talking about here is variability. It's not the constant sun or the constant cosmic rays that matter, but are these things varying in time? And if they are varying, are they affecting clouds and climate? So this is the part of the sun that you're very familiar with. This is what the sun looks like during the peak of the sunspot cycle. So these are sunspots rotating around with a periodicity a rotation period of 25 days in the equator, that's what it looks like. But the sun has another nature. This is the temperature at which radiation is emitted from the sun and reaches the Earth. So practically all of the solar constant, the warmth that comes from the Earth, is being emitted from this layer that you're seeing now. And the only difference, if I were to show this picture during the minimum of the solar cycle, it would be identical in color. These spots would simply have disappeared. So this is now another view of the sun, but now it's being viewed at 20 nanometer wavelength. And this corresponds to about 1 million degrees, and it's looking at a part of the very thin outer atmosphere, the corona of the sun, during the solar cycle. Now this movie starts at the lowest point of the solar magnetic activity of the sunspot cycle, and it's gradually building up in years towards the peak of a sunspot cycle. And it will give you a graphical representation of the change in magnetic intensity in the corona during the solar cycle. These magnetic, you can see magnetic loops and so on, and recombinations, which are ejecting actually large amounts of plasma from the surface of the sun, and this is streaming out through the solar system, and it's responsible for modulating, among other things, it's modulating the intensity of cosmic rays on Earth. So the question is, there's clearly very big visual differences that you see here between the magnetic activity when the sun is quiet or very active, and the question is, does the sun do that on a regular, just an 11-year cycle, or does it do it stochastically over long periods of many tens of years or hundreds of years? And the evidence is that it does. We don't know why, but for some reason the sun's magnetic activity varies over these timescales. I have to be very careful about time. Colin, what time is the end of the talk? Sorry. All right. Okay, so cosmic rays. Cosmic rays are protons, mainly protons. They're produced by supernovae in the galaxy. They may, after 1 million years or so, traveling through the interplanetary, intersolar magnetic field, they arrive at Earth. And when they arrive at Earth, they collide somewhere in the top of the atmosphere, at the bottom of the stratosphere, and produce showers of secondary particles, of which the most penetrating, the muons, get down to ground level. So the cosmic rays are responsible for essentially all the ionization in the chamber, all the ionization in the atmosphere, other than the contribution from natural radioactivity over land. They have a tiny energy input into the Earth's atmosphere, something like a billionth of sunlight, so they're equivalent to the energy of starlight. It's totally negligible energetically, but because they control the ionization in the atmosphere, they could have very important effects in principle. Now, how do we know what the past variations of the cosmic rays are? We know this because when they collide in the atmosphere, they create carbon-14 or beryllium-10. Carbon-14 is oxidized and can get locked into the carbon cycle and get into tree rings and then can be analyzed as you go back in time. Beryllium-10 settles in ocean sediments, or it can settle in snow and can get compacted down into ice cores. And then when the ice cores are drilled, by analyzing the the beryllium-10 versus depth, you can reconstruct the past intensity of cosmic rays. So now let me show you a few things on solar climate variability. There's a lot of observations of this, of various forms, and I'm only going to show 3 or 4 or something plots, just to give you an indication as to what these measurements look like. The most famous association of solar variability and climate variability is the so-called Little Ice Age, when the sunspots essentially disappeared over this 100-year period, and it's associated with very cold climate, certainly in Europe, but also of the rest of the world. The signals of this so-called Maunder minimum or Little Ice Age have been seen everywhere. But the association that seems to occur is that when the sun is inactive, which means low sunspots or long cycle length, that's the space between two of these peaks, then it's associated with a cool climate, and then an active sun is associated with a warm climate. There was a second peak period here in the sunspot cycle, when the sunspots were very weak, and that's known as the Dalton minimum. And it's very interesting. I'm only pointing that out because there's strong evidence that the sun is behaving. It started to behave rather like it was in the Dalton minimum. We don't know whether that's going to continue, but those are the indications at the moment. Okay. Now, there have been a huge number of reconstructions. This is a reconstruction of temperature over the last 1,000 years. This is the timescale. There have been a huge number of reconstructions of this, and they vary in their findings. But they all rely on climate proxies. And the general observation is that there was a cold period, the Little Ice Age, and a warm period, known as the medieval warm period. There are also direct thermometer measurements from so-called boreholes, which also confirm that this was a very cold period and this was a warm period. So these are actually thermometer measurements deep in the ground, very precise thermometer measurements, and they confirm this general pattern. Now the second plot here shows over the same period the variation of cosmic rays. It's inverted, so these are high cosmic rays and these are low cosmic rays. And there's a general association, as you see a dip here and a peak here, which is shown here. In fact, there are many, many very detailed temperature reconstructions which even show up this fine grain. These are cosmic ray intensities, and this is a climate proxy. This is actually glacial advance in tropical Andes. And this shape, corresponding to cold climate here and warm climate here, is reflected very much in this. This is another plot along the same lines. This is now 2,000 years. And the same association of cosmic rays, the blue line, with climate, the red line, this is temperature in Central Europe, seems to hold up. Okay, so that's over the last 1,000 or 2,000 years. And the question is that just an anomalous behavior of the sun, or has the sun done this before, gone into this quiet state, this magnetically quiet state? And the answer is it's gone into it many times. This is only over the last 6,000 years. This is the Little Ice Age, this is the medieval warm period, and this is a measure of solar activity. It's actually exactly the cosmic ray variations over this period, measured in two different ways, and they both agree with each other. And this quiet state of the sun has been repeated again and again and again, a dozen times or so over the last 10,000 years. So the grand minima, this behavior of the sun is not at all strange, it's normal behavior. Now, are these changes associated with climate? Well, there are quite a number of observations that say they are, and this is one of them. This is one of the clearest. But this is so-called ice-rafted debris. This is measured by Bond and his collaborators. They have measured sediments in the North Atlantic Ocean due to icebergs which have drifted out into the North Atlantic and rained down the small grains and so on that they ground out when they were part of glaciers. So these are examples of these ice-rafted debris which rain down, build up a sediment, and the sediment is drilled up as a core very carefully and then analysed versus depth. The coloured lines in both these things measure cosmic ray variations, and the solid lines measure the variation in this ice-rafted debris. This corresponds to very cold, lots of icebergs in the North Atlantic, and this corresponds to very few icebergs in the North Atlantic, and this is roughly a 2 degrees C temperature variation of the surface temperature of the North Atlantic. And there's a very, very clear association of these things. So somehow this cosmic ray intensity is associated with the temperature of the North Atlantic. This is, I think, the final one I'll show you. But this is another example. This is a stalagmite that was analysed in Oman, which is presently arid, but between 6,500 and 9,500 years ago, it was very wet, and stalagmite grew in the cave there. It's been dated by thorium dating, and a particular stable isotope of oxygen, oxygen-18, the variation of that is shown in the blue curve here. And as I say, it's been dated very carefully with uranium-thorium dating. The grey curve is showing an independent measurement of cosmic ray intensity measured by California bristlecone pines. And you can just see for yourself the incredibly close association of these two sets of data. Now, there's some tuning in this data within the small errors allowed by the uranium dating. So there is some wiggle matching, as it's called. but the association is quite remarkable. And this is a blow-up of this little period here. So clearly, over this period, somehow solar or cosmic ray forcing was influencing very strongly the rainfall in this region. Right, so this was showing an association of cosmic rays with rainfall in the Indian Ocean over this period, 6,500, 9,500 years ago. Now, I'm going to mention a few aspects of solar variability in the 20th century because that obviously interests people, whether there's any effect of current climate change, and by current I mean 20th century, and the last decade due to the sun. Now, the variation of cosmic rays have been directly measured in the last 50 years by counters. Prior to that, we have to rely on beryllium-10, and there was a significant decrease of cosmic rays in the first half of last century, which has been independently measured by magnetometer measurements, which have shown a strengthening of the solar wind over the first half of last century. And this caused something like a 15% reduction in cosmic rays over the first part. So there was a change there, but very little in the second half of the 20th century. Now, there have been a number of very interesting observations of the sun over the last few years, and I'll explain those in a couple of transparencies. The first one is here. There's been an observation that sunspots are weakening over the last decade. This is a sunspot. This is the Earth to scale. So these are huge holes in the solar photosphere. They appear dark because there's a strong magnetic field inside. This is the solar photosphere plasma. The plasma is pushed aside by the strong magnetic field. It's a few thousand Gauss typically. And it appears darker because it's a slightly lower temperature than the surrounding photosphere. It's not dark, but it just appears that way. Now, some exquisite measurements have been done over the last few years of the magnetic field in that region and the temperature in that region. And this is an example of the raw data. This shows the so-called Zeeman splitting of a certain ion line, and in 1991 the splitting was wider than it is in 2002. This is because the magnetic field has decreased, and it's the magnetic field that's determining the separation of these spectral lines here. Now, there's another observation here, and this is an OH molecule which is very temperature sensitive, and the temperature has gone down in 2002. The temperature of this region has gone up, and it's reduced the OH, and that's shown here. When these data are put on a time series, what you see is this is the magnetic field in the dark region, the umbra of a solar sunspot, and it's systematically going down. Now, these authors observed this in 2005, and this is definitely a failure of the peer review system because their paper was rejected as being impossible. In fact, it's continued, and it's now been published here in 2009. And if you extrapolate this, the prediction is that the sunspots could even disappear. There could be no contrast between the sunspots and the photosphere by 2015, which is essentially what happened during the Maunder minimum, that period of very cold climate in the Little Ice Age. Now, completely independently, the last solar cycle, or is it independent? It's probably not independent. The last solar cycle, cycle 23, was exceptionally long. This periodicity, not only the peak, this is showing the total solar irradiance versus time. These are satellite measurements measuring the brightness of the sun. And paradoxically, the sun is a little bit brighter when all the sunspots are present. They're overcompensated by the bright regions, the faculae nearby. But it's about 0.1% brighter than during sunspot minimum. Anyway, this is the solar cycle, and it's a long cycle. This cycle is exceptionally long. It's actually shown here. This is 14 years. The average solar cycle is 11 years. And this is the last very long one like this, which was actually in the Dalton minimum. So the sun seems to have a very long solar cycle, and this very weak solar activity is reflected in high cosmic rays. When the sun is at the peak of the sunspot cycle, it gives a minimum in the cosmic rays. This top plot is measuring cosmic rays versus time, and you see the anti-correlation between the two. This is the so-called solar modulation of the cosmic rays that reach Earth. Okay, but that's not the end of it. Okay, this period here, from here to here, a satellite has been measuring the spectral irradiance change. So not just the total solar irradiance, but the spectral change. And that's shown here, and it's between, well, 200 to 700 nanometers. All of the IPCC models have been using the so-called lean model, which has assumed this kind of variation for that period, namely that there's essentially a uniform change in spectral irradiance over that wavelength interval. Now, it's just very recently, in fact in the last year or so, been measured for the first time, and this is the answer, the blue curve. This is what the true solar spectral irradiance change over this period is, and it bears nothing, no relationship whatsoever to what's been used so far in all the models. What is seen is a very, very big shift in the ultraviolet region and a negative shift in the visible region. And when this is put together, this band here, anything shorter than this is essentially absorbed high in the stratosphere, and only this part can get down to low altitudes. So the net effect of this, when all this is put in, it's been modeled by Haig, and in the previous lean model, the forcing at the tropopause, essentially the lowest part of the atmosphere, would have been plus 0.08 watts per square meter. But when this true spectral change is put in, it finds that the magnitude is right, but the sign is wrong. Okay, so it just shows how little is understood about the sun. And if this is confirmed, and we have to say it's only over a short period, we really need to see this over a full solar cycle. But if it's confirmed, then the models may have the wrong sign for solar irradiance forcing. It may be a cooling effect at high solar activity. So that means that the present IPCC calculations may be wrong for the solar cycle variations. In other words, that beautiful agreement between the sea surface temperature and the solar cycle, it's a beautiful agreement. The only problem is it's the wrong sign. So it's a beautiful disagreement. We just don't know what's causing the solar modulation in the sea surface temperature. It also means that that small warming at the beginning of the century is actually a small cooling. So it makes the discrepancy between the prediction, the model prediction, and the actual observations much weaker. And it's already poor, but it makes it worse. So I think we just have some huge question marks about what is the solar contribution in the century. And this is only referring to the irradiance variation. It's nothing to do with the cosmic ray contribution, but clearly we have to, if there truly is a solar effect on the climate, there's some big parts that are totally missing at the moment that we just don't know about. Okay, atmospheric aerosols. We're almost into the cloud experiment now, but aerosols are ubiquitous in the atmosphere, but they're extremely important. They have a direct effect. This is when you look at the mountains after a sunny day, the haze that you see is aerosol building up in the atmosphere. So they scatter sunlight. Now, they also have a more important climatic effect, and that is if you take an unperturbed cloud, a standard set of aerosols, and then add aerosols, you actually distribute that amount of water over more droplets, and that has the effect of making the cloud brighter. So it has an increased albedo, and more importantly, in fact, it has an increased lifetime. Those droplets are much less likely to coalesce, and the cloud will live longer and manage to reflect the sunlight for a longer time. So that's the effect of adding aerosol. And this is a photograph, I mean, you recognize this coastline here. This is a photograph of ship tracks in the North Pacific. These are aerosols which are being thrown up by carbon aerosols thrown up by ships, which are seeding clouds which persist. So you can see that although there are plenty of aerosols in the sky, there aren't sufficient. And when more aerosols are added, the sky gets brighter. Now, only very recently it's been appreciated, and it's still not quantified properly, but aerosols are also having a strong effect on deep convective clouds. Those are so-called stratus clouds, with very weak convection. These are deeply convective clouds. When you take a pristine cloud, in other words, very few aerosol, the cloud tends to rain out very quickly, and it gets very weak before it gets to high altitude. So very little water vapor is carried up. If you add pollution, then the droplets are much smaller. They don't coalesce. The cloud gets up above the freezing point. There's much more, the freezing can occur. There's much more invigoration from the extra latent heat that's emitted by the freezing. And the cloud carries the moisture much higher. And there's much high altitude moisture, electrification occurs, stronger convection, and so on. And this has a very big effect on transporting water vapor to high altitudes. And this is the mechanism. These are the mechanisms, particularly in the tropics, by which the high atmosphere receives all its water vapor. So any effect on the convection of water vapor in these deep, highly convective clouds has a very important effect. So there have been observations now to show these effects occur, but they're really not quantified and not understood, and they're not in models. Cloud models very, very rarely include aerosol-type effects, but the aerosols are really controlling the properties of these clouds in a very, very strong way, and they can't simply be represented by white boxes that reflect or absorb radiation. Okay, let me skip over this. Well, it's a very interesting observation, but let me say it very quickly. This is a map of lightning measured by satellites. Lightning occurs very, very strongly over land because it's very dependent on high updraft velocities in convective clouds. It's very weak over the oceans. On the other hand, rainfall is very much over the oceans. It's dominated over the oceans. So there's a fundamental difference between continental and marine rainfall. And the difference is the vigorous convection that occurs due to the temperature contrasts, but also the aerosol loading that's very different. It's very low in the marine regions and it's very high over land. And this is a sort of graphic representation as to what kind of differences you can get in these cloud properties. Okay, where do these aerosols come from? There are two sources essentially. They're known as either primary aerosol or secondary aerosol. Primary correspond to particles that are emitted directly from the Earth's surface. So sea salt is an important one. Bubbles burst, create sodium chloride, which is wafted aloft by winds. Biomass burning is very important for carboniferous aerosol, direct particles into the atmosphere. Dust is also important. And industrial sources are also very important, around cities and so on. There's a huge number of aerosol created by industry and by cars and so on. The second type of aerosol is known as secondary aerosol, and this is where vapors are emitted, either from anthropogenic sources or from volcanoes or from vegetation or from phytoplankton. And this creates vapors which may get converted by the sun, by photolytic reactions, into condensable vapors. And these can form aerosol from so-called gas-to-particle conversion. Now that gas-to-particle conversion is shown here. And the reason I'm focusing on this, because this is what cloud is measuring in the first step. So it involves trace vapors. They're very, very low concentrations, well below parts per billion in most cases, typically a few parts per trillion of the molecules, one in a million. These may condense, form a cluster, which when it exceeds a certain critical size can grow by further condensation or even coagulation with smaller particles and grow to the size of a cloud, where it can seed a cloud droplet, which is above about 50 nanometers. This process is strongly dependent on the concentration of vapors available, which is controlling this growth rate, but also it's also strongly controlled by the pre-existing aerosol. If there's a lot of aerosol that exists already, then these essentially scavenge these before they get to a size to change the number of CCN. So it's typically remote marine areas where the aerosol loadings are very low, where this process, this gas-to-particle conversion, can create new particles. And these things are all brought down by various sink processes, either precipitation, dry or wet deposition. Typically aerosols only last a few days to a week in the atmosphere before they're rained out. So these aerosols have to be produced on a continual basis. Now, the question is, well, okay, before we get to that, is that an important process? What's the relative contribution of these so-called primary direct aerosol and the secondary aerosol from vapors? And the answer is essentially shown in this model, or this is one particular calculation. This is the CCN fraction that's due to gas to particle conversion. It's very high, this is the percentage, it's very high in clean regions, in marine regions. Conversely, where the regions are polluted, they're mainly primary production of particles. This is carboniferous aerosol. And this is the Southern Ocean production where it's very windy, and this is sea salt production. Okay, now, so it is an important process. Gas to particle conversion is responsible maybe for about 50% of the aerosol, CCN, in the atmosphere. It's quite remarkable that such an important process is so poorly understood physically, because we don't even know what the vapors are that are responsible for the nucleation. It's thought, it's more than thought, it seems that sulfuric acid is always involved. It's a very low vapor pressure, it's very rare in the atmosphere, part per trillion or less, but it has very, very low vapor pressure, and it seems to be involved in all the nucleation. But other vapors are also thought to be involved, that ammonia and organic materials, but they're really not, they're not properly understood, because so far nobody, okay, so this cartoon is actually showing this molecules which condense to make these so-called critical clusters consisting of a few molecules, which then by further condensation become a sort of liquid drop type aerosol. But this critical step, nobody so far has actually measured molecule by molecule how this thing grows from a vapor. I say so far, we've actually done it for the first time in cloud. The combination of the cloud experiment, the chamber that I'm going to show you, plus some state-of-the-art instrumentation. I mean, these are spectrometers, but they're being developed all the time. We've actually measured molecule by molecule the growth, and we know what at least some of the vapors are that are involved in this process now. But there's a very important step here, and that is that when these embryonic clusters form, they're actually very unstable. Once they cluster, they're much more likely to evaporate than to grow further. So there's actually an energy barrier, and when the cluster is on this side, it will evaporate rather than go further. And it has to exceed a critical size, which is actually an energy barrier. Once it exceeds that, then it will continue to grow. So this very, very first step, which is the step that Cloud has recently measured, is the critical step in the birth of these particles that can then in principle grow to become the seeds for cloud droplets. And then finally, I've just referred to the molecules involved. The effect of ions from cosmic rays may also help overcome this energy barrier, but that's also been very poorly known prior to our measurements. Now, I'm going to get into the experiment now, and I have to apologize because we've just, in the last 3 weeks submitted a paper to a certain journal that is very, very sensitive about not pre-releasing results. So I'm going to give you some flavor as to what we're measuring in cloud, but I can't show you the most interesting things, because if I did, that would torpedo our chances with this journal. So I'm going to apologize right now, but I hope that doesn't spoil the talk for you. So what is cloud? Cloud is a large chamber, 3-meter chamber, and it's located at CERN. It's a very strange experiment. I think, to my knowledge, it's the first time a high-energy physics accelerator has been used for climate research. But what we've done is build a very large, clean chamber, and we expose it to a particle beam from a CERN accelerator. The idea of the particle beam is that it's an artificial source of cosmic rays. I mean, the disadvantage of doing an experiment in the laboratory, of course, is it's not the atmosphere. The problem of doing the experiment in the atmosphere is you observe something and you don't know what caused that change. When you do it in the laboratory, you have a little knob that says beam intensity, and you turn that and see a change in your experiment. You turn it down and you see your experiment go the other way. So you have a very, very clear understanding as to, you control all the parameters. And the parameter that we control at CERN with the beam is the cosmic ray intensity. And we vary it between the intensity at ground level up to the top of the atmosphere, which is about 2 orders of magnitude higher because of the low shielding of the air. So I'm going to just step through bits of pieces of cloud. This is the cloud chamber. It has a lot of thermometers to measure its temperature. It has mixing fans to make sure the contents are uniform. It's surrounded in a thermal housing that maintains the temperature to 1/100th of a degree precision and stability. And this is controlled by an airflow which is sent round with a precision thermoregulator unit. We also have an electric field. This is a transparent electrode on the top and bottom. We put plus or minus 30 kilovolts on that. And when that's on, we sweep all ions from the chamber in about 1 second. So if we want to measure neutral processes alone, we have the electric field on. When we want to measure the effect of the beam, we turn the field off. We then have a UV system which is quite novel. It involves a lot of quartz optical fibers which carry in UV light, which irradiate the chamber in a column of UV light and simulate photolytic reactions. We make the sulfuric acid in the chamber by converting oxidizing sulfur dioxide in the presence of ozone. We connect it to a gas system. There's a very special gas system that we've designed that puts in ultra-pure air, humidified air, trace gases, and so on. Just as an example, we can't purify air well enough for our purposes. So we make synthetic air from liquid nitrogen and liquid oxygen boil off, and any of the backgrounds that bother us are frozen out by this, so they don't get into the chamber. We expose the thing to a particle beam from CERN and measure it in a counter-hodoscope, and we continually sample through sampling probes that project into the chamber through a lot of mass spectrometers and various other instruments. We continually sample small quantities of air, and the experiment is essentially like cooking. We prepare all the ingredients in a big chamber and then simply follow how it cooks with time, add the beam and see what happens, and we just follow it for several hours and follow the growth of these particles and so on, or whatever's happening. And let me show you a few pictures to give you a flavor for it, and then I'll show you a bit of the data. This is what the chamber looks like on the outside when it arrived, before it was put in its housing. This is a 3D view. These are the sampling probes connected through valves to instruments. This is the transparent electrode, the fans, the UV system, and so on. And here are some photographs. This is what it looked like last summer. This is the thermal housing, various instruments that are around it. The beam comes in from this side and is about 2 meters across, when it 2 by 2 meters when it crosses the chamber there. These are the UV fibers on the top surface. This is a picture of what the light looks like inside. This is the feed-through design of these things. This is the inside of the chamber. This is the transparent electrode. We have these are the high voltage standoffs. These are made of zirconium oxide, which has no surface charge. It has a small conductivity. We've been very careful that when the electric field is turned off, there is zero residual electric field due to surface charges on any insulators inside the chamber. This is the bottom manhole cover, and this is a view up through the bottom manhole cover of with a fisheye lens of these are the UV fibers. This is an individual fiber. Reflections off the electropolished side of the chamber, and the bottom electrode is there. That's a thermometer. Okay, some data, and then we're finished. This is an example of one of those gas-to-particle events observed in the forest in Finland. This is time of day along this axis here, and this is particle size, 10 nanometers, 100 nanometers. And you see in early morning, and red means a lot of particles. So in early morning, there was a big band of particles in this size range. And then sometime around midday, a whole host of new particles were made from small sizes, grew and grew into this band. So this is a nucleation burst. These things were only first observed within the last 10 years, and they're going on all over the atmosphere. But this is a particular observation. This is our version of that done in the cloud chamber. And here we're setting up different conditions and then measuring nucleation bursts under a different set of conditions, and we're repeating it every several hours. And between measurements, we're cleaning the chamber of aerosol. So we start with clean conditions, and then we're repeating different measurements under different strengths. This is what a typical run looks like when we're doing an online measurement. So these are the control parameters. Always this is time running along this axis here. We start the run by opening the UV lights in the chamber. When we do that, we set in motion a set of the creation of sulfuric acid. And this is the rise of sulfuric acid in the chamber, and this is 3 parts per trillion concentration in the chamber. Now, when that happens, this is measuring particles in the chamber in various counters with different thresholds. These are aerosol particles per cubic centimeter in the chamber. So this is 1,000 per cubic centimeter. You can't see it here. If I blew up the scale, you could see it. But particles start to appear, and there's a constant production of particles. These are particles, stable aerosol particles, being generated by this sulfuric acid in the chamber. At this point here, we turn off the clearing field. So cosmic rays have always been going through the chamber. There's no beam, but cosmic rays have been going through, but they haven't been leaving ions in the chamber. The ions have been swept out very quickly. Now the ions are allowed to sit in the chamber, and now they can nucleate new particles. And you see a very sharp increase in the production rate of these particles. This alone is direct evidence of ion-induced nucleation. And if you can very quickly measure the gradient difference between that and that, you can immediately see what the ion enhancement rate is due to cosmic ray ionization. Now, at this point here, we then turn on the CERN pion beam at a certain intensity, and you see another sharp increase in the production of particles. And this is it's basically producing a higher ionization concentration in the chamber, and that's what you see. And these are various sulfuric acid clusters, which I'll show you in a moment in the next slide, couple of slides. Okay, so one of the very important instruments that we've got in this chamber that's allowing us to measure the molecular composition of these clusters is an instrument called the apitoff. And this, for example, is a spectrum of a trimer of sulfuric acid. There's 2 sulfuric acid molecules and 1 HSO4 minus ion. So this is actually a trimer where 1 hydrogen has disappeared, and that's why it's charged. The main peak is the primary isotope of this trimer. But there are 5 peaks here, and they actually correspond to the different sulfur and oxygen isotopes of this trimer. So not only, we don't simply measure the mass of these particles, we measure that the isotopic satellites are exactly as they should be, and we can resolve ambiguities where 2 things normally have the same atomic mass. And just to show you the resolution, this is a particular cluster here, which is labeled there. This is the measurement. This is 1 atomic mass unit, and this is the prediction based on the known isotopic ratios. So we have extremely precise measurements of these clusters, and this is reflected perhaps in this next plot. This is a measurement of clusters during a nucleation event. This is a binary sulfuric acid water nucleation, and what you see here is 1, 2, 3 sulfuric acids, 4, 5, 6, 7, 9, 10, 11, and so on. So this is 10 sulfuric acid molecules. This one here is 10 sulfuric acid molecules plus 1 ammonia. So we know exactly what the ratio is of the ammonia and the pure acid and so on. This is where we added ammonia to the chamber, and the 10, actually this is 9 sulfuric acids with 9 ammonias, 8 ammonias, 7 ammonias, and so on. So all these data are available to us, and they're all part of this paper. And I would love to show you some really good plots now, but I'm afraid I'm going to show you the summary transparency, which is here. All right, so what's the summary? There's substantial evidence for solar climate variability in the pre-industrial age, but there's no established mechanism. These variations of the climate that are solar-induced are comparable to what's been going on lately. I'm not saying whether they're bigger or smaller or whatever. They're comparable. And we have to understand those if we're to understand properly what's going on with the current climate change. I think the solar contributions to 20th century climate change, they're showing some big surprises. They're poorly understood. We may or may not know the correct sign, and we may or may not have an indirect contribution, such as from UV or from cosmic rays, that is just totally unaccounted for at the moment. Cloud is going to hopefully settle the question of whether or not cosmic rays have any climatically significant effect, but we also need to understand whether the UV is having an effect as well. We've just submitted our first paper, and there's a number of firsts in that paper. We've made the first time this measurement of the ratio of ion-induced to neutral nucleation, and it seems to be a very strong effect. We've measured the molecular composition of these critical clusters for the first time, and this has given us a very clear insight into both binary nucleation and the so-called ternary nucleation involving three components. Ammonia definitely is having an effect, but there's still more to find out, much more to find out. And in fact, in the summer, we're going to be adding organic vapors characteristic of what fir trees produce, and put those into the chamber and see the effect of organics on this nucleation process. Now, I have to stress that these effects that we're seeing already with cloud only relate to the very small few nanometer size aerosols. They say nothing about CCN, because they are not at the size where they can seed cloud droplets, but it's the critical first step. And if there's an increase in the nucleation rate, there will be some effect, depending on what the conditions are, with CCN as well. But we haven't gone up to CCN sizes yet. And then finally, I think, in my opinion, it's very important that we have to quantify what the microphysics is, not just the big picture, but really the microphysical processes, which are not well quantified and not well understood at the moment. We've got to quantify how those affect clouds and how the climate may be influenced by solar variability. And until we do that, I think we'll have very large question marks about what our understanding is of current contributions to climate change. So thank you very much. What? Oh, thanks.
So there'll be questions.
On one of your slides, you had dimethyl sulfoxide going to sulfur dioxide. That doesn't happen.
What, sorry?
Dimethyl sulfide?
Yes.
It's oxidized by ozone to dimethyl sulfoxide and then eventually on to dimethyl sulfone. Dimethyl sulfide is a very efficient scavenger of ozone. So I've seen that a lot in papers and things. It's just flat out wrong. It doesn't happen.
Say dimethyl sulfide doesn't produce sulfuric acid.
It gets oxidized to dimethyl. We use it when we do ozonolysis reactions, we use dimethyl sulfide to scavenge the ozone. Second question is...
Yeah, that's an interesting statement. Yeah.
One other question is, we have all these meteors coming in from outer space. What's the role of these little particles that get burned up in the atmosphere?
I think meteoritic dust is the primary source of aerosol very high in the atmosphere, in the high stratosphere, in the mesosphere. I think it's not significant down at tropospheric levels. I mean, you can correct me, I don't know whether you're familiar with this, but it's basically not an important source in the low atmosphere.
I've seen pictures of gamma rays coming into the cloud chambers and changing into electrons and anti-electrons.
Yeah. Yeah.
The mass. Well, we got a lot of gamma rays coming from outer space. What do they do?
Let's think. We don't have a lot of gamma rays that are at the 1 MeV or greater than 1 MeV level, which is necessary by mass conservation to create a pair of electrons. So it's very, very low. I mean, these are gamma ray bursts, and there are plenty of people looking at gamma ray bursters, and there are very few of them. And also, I mean, they actually get absorbed high in the atmosphere. they're not significant at low.
Yes, thank you. Could you just say a word about what the potential impact is of the theory that you've been discussing on the extent of cloud cover between the, let's say, the low point in the cosmic ray cycle and the high point in the cosmic ray cycle? Are we talking about a 5% increase, a 10% increase in cloud cover, or what sort of extent? And what would the impact of, let's say, suppose there was a 10%, suppose you were, just take a number, a 10% increase, what would the impact of a 10% increase in cloud cover be on the climate?
Well, okay, so two questions. The second point, if there were a 10% change in cloud cover, that's hugely significant. That's a very big effect. But observations of cloud changes, there are a lot of people studying that, using satellite data and using the cosmic ray data. And it's very controversial. Some authors claim that there's strong effects. Other authors claim there are no effects. And it's really, I think that you neither established and it's not, nor is it ruled out. Unfortunately, all these studies are highly correlated because they're all using the same cloud satellite data, the ICCP cloud data, and they're all using the same cosmic ray data, but they're making different selections and different cuts and so on, and coming to different conclusions. I think it's almost impossible to pick a number out of the sky and say, that size. We just don't know at the moment. The original observation by Svensmark and company was a very strong effect. It's clear that it's not nowhere near as simple as that. It is certainly not all clouds at all times. If this effect occurs, it will be under special circumstances in certain parts of the world at certain altitudes and so on. And I think it's sufficiently unconstrained at the moment that it's almost like, I don't want to sound like I'm advertising my own experiment, but we need the cloud data to essentially point us to where the best place is to look for these kind of effects. And then it's going to be a combination of the atmospheric observations plus the cloud measurements to try and zero in and quantify what the impact is on the atmosphere. But I just couldn't actually give you a sensible number as to what it might be. If you take the original, I mean, some of Svensmark's numbers, those are numbers like 1.5 watts per square meter variation over the solar cycle, which is very, very significant. But then other people will say there's no effect. So, the first question. Well, to say that, we have to know what the change in cosmic rays has been. And, I mean, the change in cosmic rays was only over the first half of the century. There's been very little in the second half. But, again, if there's a cosmic ray effect on the clouds, it will be instantaneous, essentially instantaneous within days. But if that's happening over a period of a decade or something with a secular change, what does that do in terms of air circulation? What does that do in terms of changing current? What does that do? I mean, all these things can have time lags. I mean, ocean currents could easily add decades to it. So it could possibly be, I mean, it can't be ruled out, that you could get a forcing in the first half of last century, and the impact, the final climate impact, is only felt some decades later. I don't know. I'm not saying that's the case, but I'm just saying it's not a simple question to answer what the effects are.
The picture you showed of the ship generated clouds is very dramatic, and that seems to be effects of the order of 10%. It also occurs to me that commercial aviation has considerable impact, and I recall some similar pictures taken with the 9/11 event, grounding all commercial aircraft. They found things. Is there anything quantitative you can say about that and
from
change
the
in
aircraft?
forcing?
Aircraft?
Well, both. anthropogenic aerosol production from those two sources, from transport.
Okay, it's true that there was an observation after the 9/11 grounding of planes over the US. I think the effect was observed in the nighttime, namely there was higher infrared emission at nighttime because the clouds were present. What's your question? I'm sorry. What was it?
I seem to recall that there were aerosols. I'm sorry, that there were contrail pictures also taken in daytime. Is that?
Yes, and in fact, all these things actually are very well quantified because there are many satellites now looking at clouds and also measuring the radiation from clouds very carefully, and any of these numbers can be measured, and in fact are measured. So I think the radiative properties from clouds are probably on fairly good physical grounds, but the actual connection between those measurements and changes in aerosol, it's the changes in aerosol that aren't well understood. But once the clouds have been created, then the radiative properties are well understood. So yes, these analyses can be done, but there's essentially fundamental aerosol numbers that are totally random at the moment and not well understood, both from mankind and from natural causes.
Any more questions? Frank, you listen to this.
I gather that variation of the global cloud cover is something that's measurable now. Is that right?
Yes.
What sort of variations are there in it, and are there any systematic patterns? Never mind what it correlates with. Is there much variation? I haven't seen the data.
Well, one of those plots I presented earlier. I don't know. I can get back to it. Sorry. What's this one? Yeah. This black line here is something called earthshine. Earthshine is the measurement of the. Earthshine is a measurement of the reflection of the Earth's light on the moon, and by measuring how bright the dark side that faces Earth, how bright the dark side is, you can measure the reflection of the albedo of the Earth. It's been measured directly for this solid black line here, and then those guys actually compared it with satellite measurements of clouds and deduced that all of their data is consistent with the satellite measurements. And they then took the satellite measurements over the last 20 years or 15 years and sort of analyzed that in the context of reflection of the albedo of the Earth and came up with this number. So there are some claims from all these independent measurements, and this is from satellite cloud data, that the Earth's albedo may be changing and that there are systematic shifts. But it's not known why there are systematic shifts, but they seem to be occurring.
I was more interested in the magnitude, and you've got anthropogenic effects as +1 watt per meter squared,
yes.
So that this is a large effect compared to the anthropogenic.
It's a huge effect with huge error bars. Now, there's a feedback on top of that. The feedback may be a factor of 2, so you could say the anthropogenic warming over the period of this curve is 2 watts, essentially 2 watts per square meter, including all feedbacks. That's just the forcing. But 2 watts per square meter would double that bar, and it has to be compared with these possible changes in cloud cover. These are huge effects. But we don't know what's causing those. And we don't know whether they're real effects or whether this was flatter or whatever. But certainly, as an experimentalist, you look at these data and you say the average of all those data, and there's 1, 2, 3, 4 different sets of measurement, all would say that there's a warming trend in clouds, a net decrease over that period, which may have reversed or may not, we don't know, since 2000. Nobody knows why that should have happened.
Do we have any more questions? You can ask another question later. Do we have any other questions? If not, there will be an opportunity for people to meet with Jasper in the boardroom on the other side. There's refreshments provided there for you, and we'll continue this discussion on until about 3 o'clock this afternoon for those who wish to. Please join with me in thanking Jasper for his presentation.